I'm going to work through an example of a collision in two spatial dimensions, and it's a perfectly elastic collision between, you could think of it as being two billiard balls. So initially you are going to have ball 1 have a glancing blow on ball 2, and then after they interact with each other, after the collision, we're given the direction of velocity 1, so velocity 1 in the final state, and then for ball 2 we're also given the direction of the velocity vector for ball 2 in its final state. And we want to find what the speeds are for ball 1 and ball 2. And then once we have those two speeds, we want to go through and verify that it was in fact an elastic collision and that the kinetic energy was preserved. So some of the values in this problem that we're going to be using, we're given that the masses are equal. M1 equals M2. I'll just call that M because it's the same for both balls. 100 grams or a tenth of a kilogram. And we're given that ball 1 is initially moving along the x direction. So V1 initial x component is 5 meters per second. And then V1 initial y is the same as the two components for V2 in its initial state. So V2 initial y, all of those are 0. So basically picked our coordinate system so that the x-axis aligns with the initial velocity of ball 1. To try to simplify things, we're given that this angle theta 1 is 5 degrees below the x-axis, and theta 2 is 85 degrees above the x-axis. Okay. So my two unknowns, I don't know the speed corresponding to this velocity vector v1 final, and I don't know the speed that corresponds to that velocity vector v2 final. So we have two unknowns, v1 final and v2 final, and since it's given as an elastic equation, we actually have three equations we can choose from. We have conservation of momentum along the x direction, and momentum is going to be conserved along the y direction as well, and because it's an elastic collision, the kinetic energy can't change. Out of those three equations we can choose from, I'm going to pick the two momentum conservation laws. That's going to be a little bit easier to deal with. The conservation of kinetic energy is going to involve taking a square root to go from the v squared in the kinetic energy to just v. So it'll be a little bit easier to work with the two momentum conservation laws because they're both linear in the speed. Having said that, this problem is overdetermined. I could actually have one more unknown and still solve for it. So there could be one piece of information about the final state. Left is an unknown, and I have 3 equations that I can use. So 3 equations and 3 unknowns would be a case where I could solve and determine everything. All right, so let's look at conservation momentum along the x direction. Let's set that up and see what we learn. So conservation of the x component of momentum. We have mass of ball 1, v1 initial along the x direction, mass of ball 2, v2 initial along the x direction. It's going to equal mass of ball 1, v1 final along the x direction, plus mass of ball 2, v2 final along the x direction. And this is going to simplify a little bit. That ball 2 is at rest, so definitely not moving along the x direction. So I can throw that out. And looking at our diagram for v1 final, its x component, I'm going to be taking the cosine of 5 degrees. And for v2 final, its x component, I'll be taking the cosine of 85 degrees. And then all of the masses are the same, so I can divide those out. All right, so what do we know so far? We're going to know that 5 meters per second on the left-hand side is going to equal v1 final cosine of 5 degrees plus v2 final cosine of 85 degrees. All right, so I don't know v1 final, I don't know v2 final, and I just have one equation. So I can't solve it yet at this point. So let's go ahead and look at conservation of the y component of momentum. Let's see what we can learn from that. So writing that out, mass of ball 1, v1 initial y, plus mass of ball 2, v2 initial y. It's going to equal mass of ball 1, v1 final y component, plus mass 2, v2 final y component. And again, we're going to have some simplifications because neither ball is moving along the y direction initially. So my whole left-hand side is going to collapse to 0, and then the masses are the same. So I can divide through by the mass. So what does that tell me? That is going to tell me that the left-hand side 0 is v1 final y component plus v2 final y component. Ball 1 was moving down, so I've got minus v1 final and sine of 5 degrees plus v2 final sine of 85 degrees. So I move the v1 final term to the other side, divide both sides by sine of 5 degrees. And when all the dust settles, I know that v1 final is going to equal v2 final times the ratio of sine of 85 degrees divided by sine of 5 degrees. So now we have 2 equations and 2 unknowns. So we can go ahead and solve that for both V1 final and V2 final. So go back to our x equation, which is 5 meters per second, is V1 final cosine of 5 degrees plus V2 final cosine of 85 degrees. And I want to go ahead and eliminate V1 final. So I'm going to take V1 final equals V2 final sine of 85 degrees over sine of 5 degrees and just pop it in right there. So then the only unknown I'm going to have is V2 final. I can just directly solve for it. So it's going to tell me that 5 meters per second is V2 final. It's going to be sine of 85 degrees times cosine of 5 degrees over sine of 5 degrees plus V2 final cosine of 85 degrees. So take all the trig terms, put them together, factor out the V2 final. We have 5 meters per second is equal to V2 final. I'm going to have a sine 85 degrees. Sine 5 degrees over cosine of 5 degrees is a tangent 5 degrees. And I'm going to have a plus cosine of 85. So solving for V2 final, I should get a number out. 5 meters per second over the term in parentheses, sine of 85 degrees over a tangent of 5 degrees plus cosine of 85 degrees. I might get that to be 0.436 meters per second. And we know that once we have V2 final, we'll have V1 final. So we can go ahead and find what V1 final is as well. Find the other speed. So just writing down that relationship again. And now we can plug in what V2 final was. 0.436 meters per second times sine of 85 degrees over sine of 5 degrees. When I do that, I get 4.98 meters per second. So ball one slowed down just a tiny bit. I want to check that I haven't made some sort of mistake here. I've used the conservation of x momentum, I've used the conservation of y momentum, but I have not used the conservation of the kinetic energy. So if this is indeed a perfectly elastic collision, then the initial kinetic energy should equal the final kinetic energy. And we can go ahead and check that and have a little bit more confidence in our answer. So kinetic energy initial is a half m1 v1 initial squared plus a half m2 v2 initial squared, and ball 2 started at rest, so I can throw that out. values. The initial kinetic energy is going to be a half times 0.1 kilograms times 5 meters per second squared. It's going to be 1.25 joules. And you can check, is that the same as the final kinetic energy for our 0.436 and our 4.98. So that's going to be a half mass 1 V1 final squared plus a half M2 V2 final squared. And again, the masses are the same, so I can rewrite this and put in values. A half 0.1 kilogram. I'm going to have a 0.436 meters per second quantity squared plus 4.98 meters per second quantity squared. I'm going to go through and calculate that. A half 0.1 kilograms. Then this whole term in parentheses is 25.0 meters squared per second squared. Just like that 5 squared is going to give you 25 meters squared per second squared. So indeed, I have the same final kinetic energy as I had in the initial kinetic energy. So the collision preserved the x component of momentum, which that will always be the case for a collision, an isolated system. It preserved the y component of the momentum. And in addition, it's a perfectly elastic collision, so the kinetic energy was also preserved.